Hi, I'm Eric. Are you wondering about the Pythagorean Theorem? Maybe you are learning it in school or studying for a test. Perhaps you've been told you have to learn it, but wonder when you'll ever use it in real life. If you answered yes to any of these questions, then don't go anywhere. In this lesson, we are going to learn about the Pythagorean Theorem and some of its potential uses. Welcome to EJFullerton, where class is always in session. Let's dive right in and see what Pythagoras has to say about his theorem. The Pythagorean theorem states that for any right triangle, the area of the square on the hypotenuse is equal to the sum of the squares on the other two sides. Let's explore this further. A right triangle has two legs that form the right angle. One leg here and one leg here. Remember that a right angle is 90 degrees and is often labeled like this. The third side of the triangle is called the hypotenuse. You can identify the hypotenuse because it is the only side of the right triangle that doesn't form the right angle. It forms one angle here and one angle here, but these angles are not 90 degrees. You can also identify the hypotenuse because it is the side opposite the right angle. Looking at our triangle, let's name the sides. Now you can name the side whatever you want, but what you will typically see for the Pythagorean theorem is sides labeled A, B, and C, where one leg is labeled A, the other leg is labeled B, and the hypotenuse is always labeled C. Now either leg can be labeled A or B, so that you can switch these around if you choose. However, once you've labeled the legs, you cannot change their names during your calculations. For the next part, we are going to jump out of the digital world and into reality. Let's look at an illustration of our triangle. Previously, we labeled our triangle A, B, and C. We will continue by drawing a square on each side of our triangle. For leg A, with a side length of 1, 2, 3, we can draw a square with side lengths of 3. So this side length 1, 2, 3 by 1, 2, 3. So we have a perfect square on side A with side lengths of 3. We can do the same for B. B has side lengths of 4, so 1, 2, 3, 4 units. And so we have a perfect square that is 4 by 4 units. And finally for C, on the hypotenuse, we'll draw another square. This square has side lengths of 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So once again, another perfect square off of the hypotenuse that is 5 by 5 units. If we calculate the area for each square, we have areas of A, or A times A, or A squared. We have side lengths of B times B, or B squared. And we have side lengths of C times C, or C squared. All of this leads us to an understanding of the formula for the Pythagorean theorem. C squared equals A squared plus B squared. You may also see it written as A squared plus B squared equals C squared. Both are two ways of writing the same formula, and both are correct. Now here is proof of the Pythagorean theorem in action. We'll go back to our right triangle. And I'm just going to pull these apart just so we can see our labels. As we said, side A has side lengths of 3. So A equals 3 units. B has side lengths of 4. And C has side lengths of 5. We will write our formula out again. So C squared equals A squared plus B squared. As you know, it's always a great idea to write our formula out again and show all our work so we can just catch ourselves if we're making any errors or mistakes. What we'll do now is we will just sub our values 3, 4, and 5 in for our variables a, b, and c. So we know that c is equal to 5, so we can sub 5 in for c, or 5 squared, equals 3 for a, so 3 squared, plus b is 4, so 4 squared. We'll continue by simplifying, so 5 times 5, or 5 squared, is the same as 5 times 5, which is equal to 25. 3 squared, or 3 times 3, is 9, plus 4 squared, or 4 times 4, is 16. As we continue, 25 is equal to 9 plus 16, which is 25. So, in this equation, the left side is equal to the right side. So we can say that this equation is true. And there you have it, proof of the Pythagorean theorem. However, there's one more way that I can show you if you don't believe me already. So I'm just going to take the square off the hypotenuse. I'm going to put it out here. I'm going to take the square off of leg B and lay it directly on top of the square of the hypotenuse. And I'm going to do the same for A, except for A, I'm just going to have to cut it up a little bit. So just bear with me while I give it a few cuts. And so there you have it. You can see how the square of each leg, A and B, is equal to the square on the hypotenuse. So it just proves, as with the statement on the Pythagorean theorem, the sum of the square of the two sides, A and B, is equal to the square off of the hypotenuse, or square C. So there's another way of proving that the Pythagorean theorem is in fact true. Now, let's put it to use. Because we know the Pythagorean theorem to be true, we can use it to find an unknown length in a right triangle. In this example, we have a right triangle with leg A equal to 5 units, leg B equal to 7 units, and an unknown hypotenuse labeled C. To begin to solve for C, we will write out our formula. So our formula is c squared equals a squared plus b squared. We will continue by substituting our known numbers in for our variables. So we don't know what c squared is, so leave that as c squared. We do know that a is 5 units, so 5 squared, plus b is 7 units, plus 7 squared. As we continue, we have c squared equals 5 squared, or 25, plus 7 squared, or 49. Continuing to simplify, c squared is equal to 25 plus 49, or 74 units squared. So the area of the square on the hypotenuse is 74 square units. But we need to know the length of the side. Not to worry, all we need to do is the inverse, or opposite, of finding the square. If the square on the hypotenuse is c times c, or c squared, then the inverse function is the square root of c squared. Going back to our solution, we have c squared equals 74 units squared. So we're going to take the square root of c squared. Now remember from algebra, whatever we do to the left side of the equation, we must do the same thing to the right. So if we take the square root of c squared, we must take the square root of 74. So the square root of c squared, the square root and the squared cancel each other out, and we're left with c is equal to the square root of 74. Now, it's perfectly acceptable to leave your answer as a square root. But if you have a calculator with a square root function, you can also complete this calculation, and you would get c is equal to 8 5.6 units. But what if you know the length of the hypotenuse, but you need to find the length of a leg? Let's take a look at example 2. In example 2, we once again have a right triangle with leg A equal to 4, the hypotenuse C equal to 6, and an unknown length B. We'll start again by writing out our formula. C squared equals A squared plus B squared. We can substitute our known values in for our variables. So C is equal to 6, so 6 squared is equal to 4 squared for A plus our unknown length B, or B squared. Continuing, 6 squared is 36, equal to 4 squared is 16 plus B squared. We will rearrange our equation now to isolate B on one side. So we are going to have 36 subtract 16 equal to B squared. 36 subtract 16 is 20 equals B squared. So the area of the square on leg B is 20 units squared. In order to find the side length of B, we need to take the square root of both 20 and B squared. So as before, whatever we do to the left side of the equation, we do to the right side. So we'll take the square root of 20 equals the square root of B squared. And as we saw before, when we have the square root of B squared, the square root and the square cancel each other out. So we're left with the square root of 20 equal to B. So the length of the side, or leg B, is the square root of 20. And as we know, it is fully acceptable to leave this side length as the square root of 20. Now there's something else we can do with the Pythagorean theorem, and that is check our work. So if we are to check our work, we can start again by plugging in our three values now for our variables in the equation. So C squared equals A squared plus B squared. As before, C is 6 squared equals 4 squared plus, now we know the square root of 20 squared. And calculating this out, 36 is equal to 4 squared is 16 plus the square root of 20 squared. So as before, the square root and the square cancel each other out, and we're left with 20. As we simplify, 36 is equal to 16 plus 20. 16 plus 20 is 36. So the left side of the equation equals the right side. And so we know that this statement is true, and we know that our previous work in calculating the square root of 20 for the side length of B is correct. Finally, you might ask, but how would I ever use this in real life? Why do I need to know it? Well, here is a real-life example from my life. A couple summers ago, as you can see, I was building a small deck in our backyard, a quiet place by the river where my wife and I could enjoy the weather, read a book, or have some friends over for a barbecue. During the construction, I wanted to make sure that the sides were perpendicular to each other, meaning that they formed 90-degree angles in each corner. So what I did was use my knowledge of the Pythagorean theorem to help me form these 90-degree corners. I knew that a triangle with side lengths of 3 and 4 would have a hypotenuse of 5. So I measured 3 units on one leg, 4 units on the other. Then, using a length of board as the hypotenuse, I completed my triangle. If the length of this board was 5 units, then, using the Pythagorean theorem, where c squared equals a squared plus b squared, I can substitute my values for my variables. So c squared is 5 squared, plus a is 3, so 3 squared, plus b is 4, so 4 squared. You might remember this example from the start of the video. 5 squared is 25, equals 3 squared, which is 9, plus 4 squared, which is 16. So continuing, 25 equals 9 plus 16 is 25, and as we know, the left side is equal to the right side, so therefore this statement is in fact true, which also means that my triangle must be a right triangle, and my angle where A and B meet is 90 degrees. Repeat for the other corners, and voila! A beautiful place to rest and relax. A real-life use for the Pythagorean theorem. The same idea could be used when building a house and making sure that the walls do in fact stand up straight. Before you go, be sure to visit our website, EJFullerton.com, to download our notes and slides from this lesson. I hope you learned something with us today. If you haven't already done so, please subscribe and like this lesson. It's only a couple clicks for you, but it means a lot to us. And share with your friends. After all, sharing is caring. Do you have a mathematical or science concept that you would like to see explained? Please leave a comment and let us know. If we make a video from your suggestion, we will give you a shout out in the video and description. I'm Eric. Until next time, take care and keep learning.